Hola, buenas tardes tengan ustedes. En nombre de la doctora Cecilia Nogués Garrido, presidenta de la Ciudad Mexicana de Materiales, les damos la más cordial bienvenida a esta sexta sesión y última sesión del curso de Microscopía Electrónica de Transmisión que organiza la Sociedad Mexicana de Materiales en este ciclo de conferencias de la sexta edición de la Escuela Virtual de Técnicas de Creación de Materiales. Vamos a cerrar este curso con la presentación del doctor Tim Eldred, Ph.D., que él es especialista de la compañía JEOL. Dear team, thank you so much for agreeing this presentation, this talk. Thank you very much. Antes de comenzar, voy a leer una breve semblanza del doctor Tim Eldred. Tim es ingeniero de aplicaciones de JEOL Estados Unidos, especializado en microscopía con corrección de aberración y 4D STEM. Obtuvo su doctorado en Ciencia de los Materiales en la Universidad Estatal de Carolina del Norte, especializándose en la estructura local y los defectos en ferroeléctricos y piezoeléctricos. Tras su graduación se incorporó a Protochips como ingeniero de aplicaciones, especializándose en microscopía in situ. Sus proyectos actuales se centran en la formación y la educación en microscopía, ayudando a los usuarios a optimizar sus experimentos y procedimientos. Sí, entonces, antes de comenzar, recuerden que tenemos unos mensajes para ustedes, los que ustedes ya habitualmente conocen, pero que es necesario recordárselos. Entonces, recuerden que para que ustedes obtengan una constancia de asistencia a este curso, ustedes deben estar debidamente inscritos en la escuela virtual, asistir y permanecer el 80% de las sesiones, que son 6, esta es la última. Cambiar el nombre del perfil en Zoom al formato apellido paterno, apellido materno y nombres. El control de asistencia es únicamente por Zoom. Los resultados finales se mostrarán a partir del 23 de febrero. ¿Okay? Recuerden que por respeto al ponente, favor de usar el chat y micrófono solo para consultas sobre el curso. Agradecemos su atención y colaboración. This talk will be in English. And Tim, thank you very much. And, and, and can you begin?
Hello, everybody. Thank you so much for having me here at this virtual conference. As he said, my name is Tim Eldred. I'm one of the applications engineers at JEOL, which means my life is wandering around helping people optimize their experiments, helping them with training, and talking about microscopy. So it is a pleasure to have this audience here today. What I'm going to be talking about over the course of this, as I'm getting my laser pointer up, is advances that JEOL has been making in taking control of both the environment of your experiments, unlocking new materials with that techniques, and also advances in dose management. But before we get that, just to give a little bit of context, JEOL is a analytical products company. We do a whole bunch of different instrumentation from TEM to SEM all the way down through NMR, sample prep. But what we're going to be talking about today is we're going to be focusing in on TEM, and specifically on the role of analytical microscopy in material science. So there are probably some material scientists in here who don't do microscopy. There are probably some microscopists in here that aren't as dedicated to material science per se. I kind of want to speak to both groups over the course of this talk. To provide a little context on why the material scientists might want to put some ideas in their head about microscopy, but also to let the microscopists know some new things that they're able to work with, some new possibilities that are out there. So context. SEM is one of the great ways to actually get high resolution imaging in 3 dimensions, and it's great. Ultra high resolution SEM from JEOL, we're looking at about 0.5 nanometer per pixel. It's a very good resolution. But it's very good sampling, but the spatial resolution has a little bit to be desired when we're talking about TEM. So when I talk about high-end TEM, the context is this is the size of the image that we're talking about. We're talking about high atomic resolution data where instead of being half a nanometer per pixel, we're talking about 2% of a nanometer. We're talking about 2 picometers a pixel, 20 picometers a pixel. And this unlocks a whole lot of understanding of your materials in ways that without TEM, you can't really interrogate. For resolution, what we're talking about is 48 picometers of spatial resolution. We can actually resolve dumbbells in gallium nitride down one of the more challenging zone axes. And again, this just allows high precision, high accuracy research done on the atomic level. Why is this sort of important to material science? So there are a lot of different techniques that allow you to get out different information. In addition to just the atomic resolution imaging, we can do chemical mapping. We can look at size, morphology of grains, nanoparticles. We can look at the phases of these materials. We can apply this to almost every sort of material system, semiconductors, composite materials. I've done a lot of work on nanoparticles and metals, but the requirements for this are high spatial resolution. You need a quality instrument, and you need to take care of how you're irradiating material with electrons. We're going to talk briefly about several different STEM detection methods. So STEM, scanning transmission electron microscopy. I'm going to try and make this relatively easy. Annular dark field, or ADF. You can see that the detector is an annulus where the bright beam passes through. There's also bright field, where you're looking at the direct beam. ABF, where you're not looking at all of the direct beam. And then segmented STEM. If you're not familiar with these terms, don't worry. I'll be covering them in more detail where they come up, but I'm just kind of trying to introduce a little bit of the concepts that we'll be talking about. Additionally, there's a technique called differential phase contrast that I'll be talking about later. So the images that I showed earlier were ADF, where you get atomic information. With differential phase contrast, you start to be able to extract local electronic field and magnetic field information, even at the atomic level. So you can imagine, as you're looking at the atoms, you can actually see the radial electric field coming off of these positions. We'll be talking more about this a little bit later, but again, putting some things out into the open. What this also lets you do is look at higher length scale. So this is a PN junction imaged with differential phase contrast, showing the direction of the field at the PN junction. Additionally, here's an atomic resolution image where you can see the electric field around not only the strontium and titanium positions, but also these very faint oxygen positions. And so these just unlock additional methods of interrogating your data. I mentioned chemical orientation, chemical mapping. When we're looking at it in HR STEM, now we can do atomic resolution EDS. We can get chemical information about different specific sites, showing that we can decouple the strontium signal from the titanium signal. We can see the oxygen lattice and the overlap between the oxygen and the titanium. And we can get all of this at very high resolution atomic data. Putting all of this together, I like to group these things under controlling your experiment. So there's some challenging material types. So I'm going to be talking about magnetic materials, which require you to control the environment inside the microscope. I'm going to be talking about beam-sensitive materials, which require you to control the dose, the amount of electrons that your sample is seeing. And we're going to talk about automation, which is a huge topic in TEM going forward. And that's all about being able to control the microscope in the ways that you would like to. For controlling the environment for magnetic materials, I'm going to be specifically talking about field-free imaging. Motivations behind this: magnetic materials are an incredibly industrially relevant material system, everywhere from inside computers, inside motors. It's hard to think of an industry that is not touched by magnetic materials. But what we've lacked is a way to really interrogate magnetic fields at the atomic level. We can get larger scale information, but it's this high resolution data. And the reason for that is typically in high resolution STEM or in electron microscopy, there's this what's called the pole piece that your sample sits on, and that sits inside of a magnetic lens. This is required in order to, used to be required. You'd have to have a short focal length because it's inside the lens. It's harder to get shorter than that. It allowed for very large magnification, very low aberrations. It's kind of the industry standard. The problem is that that is a magnetic field on the order of 2 Tesla. And so anything that you're trying to work with where the signal could be less than that, you're never going to see it against that. It's like looking at a candle in front of the sun. That's the drawback, is magnetic materials, as you pass them through that field, you'll deform your sample. If you have magnetic domains, they will get swamped, they will get migrated, and you will also induce aberrations in the electron beam from having a magnetic sample. So what JEOL has developed is the magnetic field-free atomic resolution system, where instead of this lens that your sample sits in, there are 2 lenses above and below where the field cancels out. This is the first MARS that is at University of Tokyo in the hands of Dr. Shibata, and they've been putting out great work on it ever since it was put in there. The result is this magnetic field situation where you have this eddy in the middle, where your magnetic field is on the order of, if not less, than the magnetic field experienced on the Earth. 10,000 time reduction in your magnetic field from a traditional instrument. This allows us to have short focal distance, high magnification, low aberrations, and low magnetic field around the sample. The problem that that an approach like this has traditionally led to is you have a large spherical aberration, which required the development of a higher order aberration corrector. Enter JEOL's delta corrector. This is a triple dodecapole corrector. Instead of worrying about the specific lensing on it, what we need to focus is this unlocks aberration correction up to 5-fold, which allows 6-fold astigmation. And so even in this system where now we have separation of our objective lens, we're still able to get these extraordinarily good ronchograms that are large enough for us to do atomic resolution work. This leads to imaging of materials that we were never able to do. So we have a germanium sample over here that's just for spatial resolution testing, showing we can get down to 82 picometers. We have atomic resolution image along grain boundaries, but the most important one to me is this one over here, which is literally a rare earth magnet that we're able to do atomic resolution work on. This is not something that is possible without a system like this, to get atomic resolution data on an active magnet. This allows this kind of interrogation for basically any magnetic material. And some applications for this, iron, very common structural material. Studying the dislocations in iron is a little bit problematic because, again, it's a magnetic material passing through a magnetic lens. You get distortion. Distortion causes dislocation migration. And so it's difficult to tell whether what you're seeing is how it originally was or what has happened from movement. Having this system where we do not have a magnetic field has allowed us to do heating tests on iron, where we're able to look at the migration of the dislocations, not from sample bending, not from magnetic field, but just from the heating, just from the stress while you're the tensile stress while the sample is being heated. What this has also unlocked is interrogation of the magnetic field that is experienced at the atomic level. Not just imaging at the atomic level, but understanding magnetic spin direction. So this is a sample of hematite, the antiferromagnetic behavior. This is a paper by Kono and Shibata, where they're actually able to see the magnetic spin directions on alternating layers of the hematite. This was unthinkable about even 5-6 years ago. This is a fantastic paper that if you're interested in magnetic imaging, I recommend that you take a look at this paper. But here we've again gone back to DPC. So the beam, you can imagine that an electron beam, when passing through an electric or magnetic field, experiences deflection. And by measuring that deflection, you can get information about the field that it passed through. There's more nuance, but that is the fundamental concept of differential phase contrast, is looking at beam deflections. And in this case, looking at the very subtle beam deflections caused by atomic resolution magnetic fields. One of the challenges of having a field-free sample area is backscattered electrons. In a traditional lens, the backscattered electrons are channeled back up the microscope. And the reason that's important is if you want to do elemental analysis with EDS, if those electrons are not channeled up, you end up oversaturating your detectors and damaging them, which makes this X-ray analysis completely impossible. So we had to design a new shield to go in between the sample and the detector that would allow the X-rays that we want through while also not allowing the unchecked backscattered electrons. So now we can actually do elemental analysis, unlocking another capability. And where this all comes together, and this is where I want to land, is on this magnetic tunneling junction sample, where on the same sample at the same time, we can map all of the elements that are around. We can do traditional imaging, but also we can apply magnetic fields. And in the differential phase contrast, we can see how the magnetic structure of the material changes with the application of millitesla fields. And again, we're applying fields that are on the millitesla range when the magnetic field of the lens in a traditional microscope is on the Tesla range. So previously, this would just be a fully saturated out image. So this is just the summary of the magnetic materials. And if somebody has a quick question that they would like to ask about magnetic materials, we can address that now, or there will be a much longer Q&A section at the end. I'm going to look at the chat very quickly.
There are no comments yet, Doctor.
Wonderful. In that case, I will close the chat and let me hop over to Dear PowerPoint. Please hop over to the next section. There we go. So the next section is talking about dose control. So you can imagine we have a very high energy beam, 200,000 electron volts, 300,000 electron volts, that is required for high-end atomic resolution imaging. This leads to challenges with beam-sensitive materials. Kind of the classic example is zeolites, where as you image them, they go from crystalline to fully amorphous. But other samples that you might not think of as heavily beam sensitive, sodium chloride. Over the course of doing elemental analysis, it goes from a crystalline cube to fully degraded and broken down. So what are our options for interrogating these beam sensitive materials? Traditionally, you would lower the potential of the gun. So you can imagine if you have a lower energy electron beam, you would cause less knock-on damage, where you're literally knocking atoms out of your system. You can decrease the dose. This is looking at the overall current, the amount of electrons that your sample experiences. You can maximize your efficiency. So there are some methods of analysis that are more dose efficient, so you can get the same information with fewer electrons. The problem is you still need to get the data. You still need to get the data to draw the conclusions. You can't answer the question without the data. So how do we solve these problems? Well, when you lower the KV, you have a tendency to increase your aberrations, makes atomic resolution more difficult, because you have more chromatic aberrations at that lower potential. We have cold FEG guns, which allow us to maintain a very tight energy distribution, even at the lower potentials. This allows us to retain the spatial resolution. The method that I tend to favor is just decreasing the dose. And we're going to talk about EDM, which is electrostatic dose management, for the rest of this section. This allows on-the-fly adjustment of your experiment. And because this is being the way that we solve this problem with the electrostatic shutter, the tuning of the microscope is not affected. There's no loss in your resolution. The rest of the microscope is still the same. There's no change in your energy. We're not going to talk too much about analytically efficient techniques, but there are quite a few ways to, once you've decreased your dose, still get good signal. So one of the problems with a decreased dose is you have worse signal to noise just because there's less signal. There's still inherent noise in instrumentation. But by using techniques that have good dose efficiency, like OBF STEM, high solid angle EDS, you can still get good data and you can still get the data you need at these lower solutions. So low KeV STEM imaging, we're talking about dropping the potential. We've demonstrated high resolution, atomic resolution data down to 30 keV. And to show it off on very delicate samples, we're doing it on 2D materials like molybdenum selenite and graphene. Graphene being one of the classic samples that's very easy to damage and burn through, especially with the electron beam. But when we're talking about dose, what I'm referring to is electrostatic dose modulation. So into the microscope, there's an electrostatic shutter that allows us to cut the beam at a speed of about 50 nanoseconds. Magnetic blankers are in the millisecond regime. So you can think that by turning off the beam, turning on the beam, turning off the beam, turning on the beam, by altering the ratio of on to off, these B to A pulses, you can decrease the dose by a proportional amount. You can imagine if you have a dose of A and you have half of it off, half of it on, so it's on for half the time, off for half the time, you've cut your dose in half. If you have a 9-to-1 ratio, you've cut your dose by a factor of 10. Having all of this integrated together and attached to the microscope and the control software allows us to synchronize this across multiple systems. To show how they've been able to do it, this is with IDES. This is just the same sample with 90%, 80% current all the way down to 10% and then back up to 90%. So 10% drops in dose, exact same sample. And while the sample is getting fainter, I talked about signal to noise earlier, you can see that the resolution is maintained even as we go to these lower doses, even after we alter this duty ratio, the on to off. The user interface is none of this matters if you can't use it, if it's not easy for a user to use. So it's literally a ratio. You can adjust how it's set up. You can synchronize it with different instruments. But the majority of the use, the easy use, is literally just setting the percentage. You can save and load all of your settings so that your experimentation has let's say user A is very frequently wanting to work at one pulse width. User B always wants to do their experiments at another. Great. Save your stuff. Pull up what you need, and you can work with it. If you're just looking to actually turn it down, there's actually a dimmer switch that sits on the desk. If you've ever used a dimmer switch to adjust your lights, you can change your dose. In traditional STEM, there's flyback issues. So you can imagine we're rastering across, and then our beam has to jump back. Then we raster across, and then our beam jumps back. What this ends up with is a non-uniform application of dose, shown down here, where we're overdosing this left area because it has to move back. It parks for a tiny bit, and then it goes across. This leads to extra damage to the left side of a window versus the right side, which you can see in this EDS map, how we're starting to get a substantial amount of damage and worse signal on the left as compared to the right. Well, we have this shutter. It's fully synchronized with the scope. So why don't we just turn off the beam there and then turn it on when it comes back? And so what this ends up with is a far more uniform distribution of dose, which means that the damage and degradation is far more uniformly distributed. And what this means is the sample breaks down slower. So you get a 50% decrease in signal in 60 seconds without dropping the dose at all. You get about a 50% increase just by turning it off while you're flying back. Additionally, how you actually move the probe matters. So the classical example that I was talking about is we go across, we come back. We go across, we come back. If you instead go 1, then 2, then 3, 4, 5, 6, There's nothing inherently required about this type of scanning. And what they noticed is by changing where you apply your dose at any given time, you allow the sample time to relax. It allows any thermal issues to diffuse. And so you're suddenly able to get more, you're suddenly able to image for longer with the same amount of dose, but less damage. So we're going to look at we're actually going to look at an asbestos sample. I took it out, so we're going to look at zeolites. The exact same amount of dose between two acquisitions. Under the classic scanning, you burn through the entire sample. Under the alternative, you can still make out the lattice. You can also drop the beam and have even less damage. This is just looking at apples to apples for the amount of dose. It doesn't have to be this crazy distribution. You can also scan stripes. So you can imagine that it's off, on as it's rastering across. And then you do the same thing, but you change which ones are on and off. This gives you the same information, but you're doubling the overall dose to your sample. But because you're applying it in a different way, your charge and heat that you're building up are allowed to diffuse, which leads to less radiolysis and less damage. And this, what we do to sort of look at this is, again, we're going to measure the changes in the X-ray count over time. So this is traditional. This is our best case with the true area scan where we're cutting it off on the way back. If we apply that and this striping pattern, suddenly what was a very slow decrease is now almost imperceptible decrease in some of the elements. This allows us to preserve our sample even while dosing. For some very low dose examples, these are classically difficult to image samples that we just like to include to show the kind of spatial resolution you can get when you're controlling for a very low dose. The last thing I want to talk about is how you control the microscope. So there's this image that most microscopists have where you're sitting down, depending on the generation, you're sitting in a dark room looking at a phosphor screen, or with the newer generation, you're sitting there looking at a screen, you've got your panels to control everything. JEOL has released an API called PyGem, which allows you to control the microscope with Python code. So all it is a Python library that allows you to directly interface with the microscope and do all of the imaging that you might want to do. You can design experiments. You can develop little widgets that automate things that you frequently do. And the limits are what you can think of in most ways. That sounds hyperbolic, but I just want to go over a couple of the things that people have already done using PyGem. I just want to put these out there for people to think about. What have people been able to do with it? So the eccentric helper these 4 apps were designed by a colleague from JEOL Europe. The eccentric helper contributes to, as you're tilting, adjusting the stage to keep your sample at the eccentric height. We have this, the MDS, which is allowing you to sort of regularize your image acquisition over multiple experiments, setting it up so that you have a workflow to search, focus, and record, and saving those settings to allow automation over time. Customization of the beam shower, allowing you to have more control than the microscope originally had. And this one down here is of very great interest to the community currently, because there is a push towards very high loss EELs. High loss EELs, electronic energy loss spectroscopy, has a lot of issues with aberrations that build up. This controls the lensing below the sample, allowing you to address those. You can calibrate it and you can actually shift it so that you have a different window, keeping that area unaberrated. But the one that I'm going to go over the examples that make me the happiest. Continuous alpha selection or continuous convergence angle. Traditionally, it's set by your lensing, and you have an aperture that is the final set of your convergence angle. You can imagine that aperture chooses how your beam is converging. But it doesn't have to. By changing the CL2, CL3 lenses on the grand arm, or the CL3 and objective lens on the neo arm, you can actually change that convergence angle. So Damien from JEOL Europe as well just created a simple solution where you calibrate it based off of the convergence angles of your microscope, and then you can just freely adjust the convergence angle without altering the corrector. So on the F200, it's literally just turning a knob or setting the angle, and you can just seamlessly move from convergence angle to convergence angle. Here's just a quick video that he put together. Well, it was going to be a video, but it does not appear to want to play. Go back to PowerPoint, see if I can make it go. The video does not appear to want to play, but it was just showing this outer circle is your convergence angle. If it was going to play, it would show this convergence angle moving in towards the center without adjusting this ronchogram that is in the center, showing that we're not changing the beam tuning. We're not changing the aberration correction. We're just bringing it in so that we can adjust the convergence angle. So these are the three examples that I had planned on talking about today. And I would like to open up the floor to the people who are listening remotely to answer any questions either about these topics or analytical TEM in general or JEOL instrumentation in general. This is not intended to be a comprehensive education. This is putting the ideas in your head and showing some of the more cutting edge things that JEOL is working on, sort of push the limits of what you can do with analytical TEM. So with that, I am going to turn it over, while I still have voice, to Q&A, and thank you all very much for your attention.
Thank you very much. Thank you very much, Tim. Questions?
There are no stupid questions. If you have a question that you're, worried, I guarantee somebody else is thinking of it, hoping that you will ask it.
Yeah. One question is that Paulina Hernandez question. It is possible. I'm so sorry. It's possible to create
a GUI with Python. Absolutely. So that is what we are showing here in PyGem. All of these GUIs, all of these interfaces were created in Python. None of these are built into the microscope. I've seen people design a GUI to do EDS. I've seen people design a GUI to remotely monitor the instruments and their vacuum from home. For lab managers, where they have all of their instruments reporting the vacuums, they have reporting the state that they're in. All of these things can be done as the limit is, how are you with Python, I would say.
Okay, thank you.
All right.
Eldred Sanchez question is, does JEOL offer training course for microscopists? JEOL offers scholarships. Where can I apply?
So we do some workshops. Additionally, when people purchase a microscope, the applications engineers like me show up on site to do initial training, advanced training, and optimization to help make sure that you can use the instrument to its fullest. As for scholarships, that is not my area, so I do not know, but I am not aware of anything like that. There is another JEOL rep in the chat, so if he wants to chime in, if I'm missing something there, he is more than welcome to. So I've skipped down to the next question, and it's a incredibly good question about the How can the contribution of the applied external magnetic field be experimentally separated from the intrinsic magnetic signal of the material? I believe you are referring to specifically, why do I have to go one by one? This figure here in the bottom left. So the magnetic field that they're applying, that the magnetic application has already been calibrated so they know what they're actually applying across it. That field that you are applying does influence the field in the sample. What they're looking at is the field in the sample as that magnetic bias is applied to it, like it would be in use. So during use, this material has a magnetic field applied across and back. And so looking at the internal magnetic field under these real situations is what the purpose of that is. It's not trying to separate that field from the applied field. It's trying to observe the changes in the field from the application of the external field. Biomaterials. That is another good question. The question was, what is the state-of-the-art biomaterials characterization with STEM? A lot of biomaterial work is done with conventional TEM because you're dealing with very low contrast materials, carbon. But with JEOL, we have multiple cryo solutions to allow things like single particle analysis, very low energy TEM, conventional TEM. We have a 120 keV microscope that is almost exclusively for, but not exclusively for, it's very commonly used for biological material. There are people using advanced materials techniques as well to do biomaterials characterization. There's a technique that is a emerging powerhouse in microscopy called tychography, which there is not enough time in a single talk to cover all of tychography, but people are already using it to interrogate biomaterials in STEM. So by and large, in STEM, you're dealing with cryo samples that are in vitrified ice. And the sort of the state of the art is automation to do single particle analysis or to do gentle imaging of large biological materials. But there are also pushes to use the advanced microscopy techniques, not critiques, developed by the materials community and figure out ways to apply them in biomaterial analysis. And I hope that answers your question.
Okay, thank you. Thank you very much. I am on.
We have another. Oh,
one question is, what is it?
Absolutely.
What is it? Is it transmission electron microscopy heated in the fusors?
I'm sorry, could you say that again?
What is the fusor of the electron of the TM?
How is it heated?
Yeah.
So there is, if you want to apply heat, there are several techniques to do that. There are MEMS chips where you basically apply a current across a resistor on a electronic chip, silicon chip with either a ceramic or a metallic heater in it that allows you to apply heat to a sample while it's in the microscope. These get up into the, I think 13 to 1600 C are sort of the, I think 1300 C is sort of the top end for companies like Protochips and DENS, companies that manufacture these holders. There are several researchers that are using lasers to locally heat the sample. So you can imagine you have your sample in the holder, pass a laser in, have it reflect off of a mirror onto your sample. They're able to achieve local heating. I've seen examples 1600 and higher, 1600 C, because you're only heating that very small area, not a much larger area. But additionally, when we talk about beam-sensitive materials, heating is one of the effects that we're dealing with damage. So as you're imaging your sample, you are inducing thermal damage as you're imaging. Let's get down to this describing sort of how the heat is applied to the sample and why you need to allow it to relax. This is a very difficult to quantify change in temperature. There have been a lot of efforts over the years to model it. What we're doing is just mitigating it by changing the way that we raster with synchrony, with EDM synchrony.
Okay.
But if you would like to heat it, in-situ holders or the laser heating are two fantastic methods, both of which allow you to increase the heat, hold the heat, decrease the heat, hold the heat, change your ramp rate if you would like to rapidly heat the sample. There are a lot of really great solutions depending upon what you would like to do.
Thank you very much. Jorge Roque question is, when did those change of the microscope in the alignment maintained at all times?
That depends on how you're doing it. With the IDEs, so there is the classical way to change the dose on the instrument is what's called the spot size. It changes the overall current going through the sample. That does affect the alignment. You need to have it aligned at each spot size differently. That's just classical microscopy. With IDEs, with this setup, with the electrostatic dose modulator, because all we're doing is you can imagine that the easiest way to think about it is there's a little box here, and as your beam is going through, sometimes it's just going, no, yes, no, yes. These aren't lenses. And as a result, it does not impact the tuning of the instrument. It is either on or off. So with IDEs, you have this sort of continuous control of dose that we never really had before in this community, specifically without impacting the optics. So if we, I was literally on the slide showing that as we control the dose, the alignment is maintained.
Okay, thank you. Thank you, Tim. I don't have more questions. And also, your teams, thank you very much for your spectacular presentation. We appreciate your participation in this virtual school. Thank you.
It was an absolute pleasure to be here. I want to just say there were some fantastic questions actually out of this group. I was very happy here. So I hope you all have a wonderful sort of rest of the school, and I look forward to working with you all in the future.
Okay, thank you. Yeah.
Goodbye, everybody.
Yes, thank you. I will issue you a certificate which states the following. The certificate is the following. La Sociedad Mexicana de Materiales otorga el presente reconocimiento al doctor Tim Eldred por impartir el curso Telkin Control Experimental Design in TEM JEOL's Advances in Dose Management and Control. En la sexta edición de la Escuela Virtual de Corrección de Materiales, firma la doctora Cecilia Nogues Garrido, presidenta de la Sociedad Mexicana de Materiales. Thank you very much, Tim.
Thank you so much for having me. Have a wonderful day.
Okay, thank you. Antes de finalizar, pues tenemos algunos anuncios para ustedes. Esta escuela virtual, su segundo curso va a ser el curso de microscopía electrónica de barrido, que va a impartir el doctor Alfredo Rafael Vilchis Néstor. Él es catedrático de la Universidad Autónoma del Estado de México. Este curso comenzará en un par de semanas, a partir del 2 de marzo. Entonces, ustedes se pueden inscribir, ahí está el código QR, en donde ustedes se pueden inscribir a este curso. Recuerden que ustedes ya está abierto para que el sistema para que ustedes puedan registrar sus trabajos en la edición 34 del Congreso Internacional de Materiales. Entonces, aquí está el código QR en donde ustedes pueden registrar sus resúmenes. Recuerden que todas estas sesiones en nuestros cursos son grabadas y publicadas en nuestro canal de YouTube, donde estarán disponibles para su consulta en cualquier momento. Finalmente, recuerden que la Sociedad Mexicana de Materiales está presente en las redes sociales, que ustedes ya habitualmente conocen, y en pantalla están los diferentes códigos QR. Bueno, finalmente recuerden que cualquier comentario o duda respecto a esta escuela virtual, pueden escribir a este correo electrónico escuela.virtual@mrs-mexico.rg.mx. Pues sin más por el momento, pues muchas gracias a todos por estar presentes en este primer curso y los esperamos que así lo hagan en el segundo curso de microscopía electrónica de barrido. Bueno, muchas gracias. Tim, thank you.